Hello everyone, welcome back to Deeksha Karnataka YouTube channel, and today I am going to discuss about another important chapter from your KCET syllabus, that is electrostatic potential and capacitance, and top 30 questions, most important questions from this chapter. They are very important questions. So if you have not yet started watching our top 30 series, we have already completed one chapter. Today is the second chapter, and also if you have not yet purchased our Abhyas KCET test series, where we are doing a lot of good things, a lot of good type of questions are there. So if you have not yet purchased, and if you want to purchase it, go there, go to the link given in the description and do it today. Okay, the time is running out, your KCET exam is approaching every day, so don't wait for the last moment. If you want to practice KCET for KCET test series, or if you want to prepare for your KCET exam, definitely you need to practice mock tests, and Abhyas test series is giving you that opportunity. Right now, let's start with our session today. Under electrostatic condition of a charged conductor, which among the following statement is true? The electric field on the surface of a charged conductor is sigma by 2 epsilon naught, where sigma is the surface charge density. Yes, it is a correct statement. Again, I think this statement will be false. Okay, which of the following is false? The electric potential inside a charged conductor is always zero, so this is not always zero, this is always constant, not zero. Any excess charge resides on the surface of the conductor. This is correct statement. Net electric field tangential to the surface of a conductor. This is also correct. So only incorrect statement is option B. So this is the correct answer for this question. Now next question, let's look into this. A uniform electric field vector E exists along the horizontal direction as shown. The electric potential at A is VA. So here we have a electric field, okay, and electric field at A is given by VA, and electric potential, a small point charge Q is slowly taken from A to B along the curved path as shown. So a small charge Q is taken from A to B along the curved path. Okay, so small charge Q, it is taken along this path, and the potential energy of the charge when it is at point B. So what is the potential energy of the charge when it is at the point B? Now constant electric field E is given. There is a constant electric field E, okay, and potential of A is VA. Okay, potential of A is VA. Potential of VB is not given. So what we have to do? We have to find the VB. Okay, what is the potential energy formula here? Potential energy formula, you have to remember that final potential minus initial potential into the charge. Okay, that is the formula we are interested in. Right now, what is electric field? Now it does not depend on the path, by the way, if you are confusing. Electric work done or energy stored of the charge does not depend on the path taken. Okay, sorry, they have asked you what is the potential energy at point B. At point B, the potential energy is, my mistake, at point B potential energy is just VB into Q. Okay, potential energy at B is VB into Q. Okay, and the work done does not depend on path, it only depends on the initial and final points. Okay, now what is electric field? Electric field is given by delta V by delta L. Okay, what is delta V here? Delta V is final potential VB minus initial potential VA by what is the distance between them? Distance between them is X. Does not matter which path you have taken, always this is true. So from here we can find that VB minus VA is equals to E into X, or VB is equals to VA plus EX. Okay, so this is the potential at point B. So what is the potential energy of the charge at point B is Q into VA plus E into X. Okay, so this is the potential energy, VA into E plus X. So option A is correct. Right now, let's move on to the next question. A parallel plate capacitor of capacitance C1 with the dielectric slab in between its plates is connected to a battery. It has a potential difference V1 across its plates. When the dielectric potential difference as dielectric is removed, when the dielectric is removed, okay, the potential difference and capacitance are C2 and V2 respectively. So first we have a dielectric slab placed inside. Okay, there is a dielectric slab placed inside. So suppose the capacitance, it is completely filled. Okay, so capacitance was C1. Capacitance was C1 and potential was V1. Okay, so at this stage, what was the charge on the capacitor plate? Charge on the capacitor plates is equals to C1 into V1. Okay, now if you remove the dielectric slab, what happens to its capacitance is its suppose the dielectric constant was K. Okay, then the capacitance C2 will be C1 by K. It will reduce by the factor of dielectric constant. Okay, so C2 will definitely be less than that of C1, and it is exactly 1 by K times C1. Okay, now the charge stored on the capacitor will not change. Charge stored will remain constant. Okay, charge is conserved, so Q will remain same in the second case as well, and it will be equals to C2 V2, and this is exactly same as C1 V1. So it is exactly same as C1 V1. Now what is C2? C2 is nothing but C1 divided by K into V2 equals to C1 V1. C1 cancels, so V2 is basically K into V1. So as you can see that potential increases and capacitance decreases. Okay, so potential increases, capacitance decreases. So we can see that here V1 is less than V2 and C1 is greater than C2. So this is the correct option, this is the correct answer. So option B is correct in this case. Okay, now let's move on to the next question. The electric field and potential of an electric dipole along its axis vary with distance r respectively as. So electric field and potential. So for a dielectric on the axis, the electric field is proportional to 1 by r cube and electric potential is proportional to 1 by r square. Okay, so very important. Normally they vary with 1 by r square and 1 by r, but for a dipole it is different. For a dipole, electric field varies with 1 by r cube and electric potential varies with 1 by r square. So it will be 1 by r cube and 1 by r square. So option C is correct. Okay. Now, two tiny spheres carrying charges 1.8 microcoulomb and 2.8 microcoulomb are located 40 centimeter apart. The potential at the midpoint of the line joining the two charges is. So we have two tiny charges. One is 1.8, another one is 2.8. Okay, and they are located 40 centimeter apart. That means the midpoint is basically 20 centimeter from both sides. Exactly, yeah, 20 from this side and 20 from this side. Now they are in centimeter, not in meters, so be careful. So when you have to convert it into meters, always you have to convert all the units into SI units, except when you are comparing. If you are comparing values, okay, you don't need to convert it because the conversion factor will cancel. Other than that, whenever you are calculating some values, calculating some equations, always convert everything into SI units. Okay, now what is the this is microcoulomb. By the way, micro means 10 to the power of minus 6. So what is the electric potential due to this at this point? So electric potential due to, say, this is V1, this is V2. So potential V1 is basically KQ1 by R1. So K is 9 into 10 to the power of 9. This is always there. Q1 is 1.8 into 10 to the power of minus 6. And R1 is 20 into 10 to the power of minus 2. Okay, so let's see how can we cancel it. It will be 80, this will be, we can cancel this one, 0.9. 0.9 into 9 is 8.1. 9981, there is one decimal point, so it will be 8.1 into 10 to the power of minus 1. You will go up plus 10 minus 4, 10 to the power of 4. So this is first V1. What is V2? V2 will be 9 into 10 to the power of 9 into 2.8, right? Second charge is 2.8 into 10 to the power of minus 6. Everything will be same. Division will also be same. Now, there is no square because it is only potential. In case of potential, there is no square. So again 10, it will be 1.4. 1.4 into 9 is 9 plus 3.6, so it will be 12.6. 12.6 into 10 to the power of 4. So if you calculate 10 to the power in one problem, the rest you can be rest assured that will be correct. So be careful, this will go up and it will become plus, this will go up and become minus, or you can combine these two and you can say this is 10 to the power of minus 1. So 10 to the power of minus 1 go up and it will become positive. So plus 9 plus 1 is 10, minus 6 is 4. Okay, this is how you can solve it. So now you add this. So total potential is basically, potential always gets added. It's a scalar quantity. There is no sign. So it will always be added. 8.1, 12.6. So it will be 20.7. 20.7 into 10 to the power of 4, or you can approximate this to be 2.1 into 10 to the power of 5. Okay, so 1 0, if you shift it, it will be 2.07, right? 2.07 can be approximated to be 2.1. Okay, don't worry, we have already calculated. We can see that this is the correct answer. So in this case, as soon as you get 20.7 into 10 to the power 4, you realize that there is only one term having 2, so that will be the answer, as the answer is 10 to the power of 5 given over here. Okay, 10 to the power of 4, don't afraid about 10 to the power of 4. You might think, oh, 10 to the power of 4 they are given, this is the closest answer. No, this is not the closest answer. 20.7 is nowhere close to 4.3 or 3.8, right? So answer will be 2.1 into 10 to the power of 5. Now next question. Parallel plate capacitor is charged by connecting 2-volt battery across it. It is then disconnected from the battery and a glass slab is introduced between the plates. Which of the following pair of quantity decreases? So first of all, you have to remember that there is a capacitor. Okay, you have charged it with a 2-volt battery. Okay, you have charged it with 2-volt battery, so the potential is 2 volt, capacitance is C. Now once you have charged it to 2 volt and disconnect it, and then you introduce a glass slab, okay, the capacitance will increase. Capacitance will increase to K into C. Capacitance will be K into C, whatever is the dielectric constant of capacitor glass, that by that times capacitance will increase. Now capacitance will increase, but the charge stored in the capacitor will remain same. Charge stored in the capacitor will remain same. So if capacitance increases by K times, the potential will be decreased by K times. We have seen similar question in problem number 2 or 3. In that case, capacitance was decreased, so voltage increased. In this case, capacitance increase, so voltage has to decrease. So voltage will definitely decrease. Okay, and also voltage decreases means voltage decreases means the energy stored will also decrease. Why energy stored will decrease? Because energy stored is half C V square. Okay, so if you see that if capacitance is increasing but voltage is decreasing, voltage has a square relationship with the energy. Okay, so energy will decrease. Energy will decrease because of the dependency of V square. Now let's see the answer. Energy stored and capacitance. Now capacitance, we know capacitance is increasing, so this is not the correct answer. Charge and potential difference. Now charge is remain constant, always conservative, so it is also not correct. Capacitance and charge, again this is not correct, so obviously you can eliminate this way as well. So potential difference and energy stored both are decreasing. Potential difference is decreasing by K times. Even energy stored is also decreasing by K times because it depends on V square. right? So correct answer is option D in this case. You can either use the method of elimination, that is called logical elimination, right? Or you can use your knowledge to answer. Both way it is correct. Now, if a slab of insulating material 4 into 10 to the power of 3 minus 3 meter thick is introduced between the plates of a parallel plate capacitor, the separation between the plate has to be increased by 3 into 10 to the power of 5 10 to the power minus 3 meter to restore the capacity of the original value. The dielectric constant of the material will be. So this is very, very interesting. So you have a capacitor, okay, you have a capacitor, suppose the distance initially was x, okay. Now you introduce a new slab of thickness, say t. It is given here, thickness given here, this is t. If you insert a thickness t, okay, to keep the same capacitance, you have to increase the distance of the plates such that by say some amount of y. Okay, so this is original distance x. Okay, we do not know what is x, okay, but we know that whatever is the capacitance of this plate, that is equals to capacitance of this plate, okay, and this definitely will be x minus y, sorry, x minus t, my mistake, this will be x minus t. Okay, so if you increase the capacitor by this amount, if you increase the distance by this amount, then only the capacitor is giving you the same value. Now let's see whatever is this. So by whatever this is increasing, this is decreasing the capacitance by the same amount. Okay, now let's see. You can solve it, the general method, let us establish a general method so that you can solve if similar question comes in your board exam, not your board exam, sorry, in your KCET exam as well. So what is the capacitance of this capacitor, by the way? What is the capacitance of this capacitor? Capacitance of this capacitor, you can consider this to be a parallel combination of these two capacitors. Okay, one is thickness t, dielectric constant k. Okay, another one is total distance is this x minus t plus y, x minus t plus y. Okay, area etc. is constant, right? So what is the capacitance of this? Capacitance of this is say C1, this is C2. So C1 is basically K A epsilon naught by D. Okay, C2 is epsilon naught A by D is in this case T, by the way, and in this case it will be x minus T plus y. Okay, so what is the total capacitance? They are connected in series. Okay, you can consider this to be a connection of series combination, right? So what is the combination of these two? C1 C2 by C1 plus C2. You can use this formula, or in this case I think it will be better if I use the older formula, that is 1 by C equivalent equals to 1 by C1 plus 1 by C2. This will be better for this problem. So T will go up, T by K, let us take T by K. This T by K, it should be taken as 1. Okay, and in the denominator we will have epsilon naught A, and in the up we will have x minus T plus y by epsilon naught A. So if you add them, what you will get? You will get epsilon naught A T by K plus x minus T plus y. Okay, now we are trying to establish a relationship between these quantities. And what is C equivalent? C equivalent is the capacitor of the normal capacitor with x. So C equivalent is basically epsilon naught A by x, epsilon naught A by x. So just put that value over here. So it will be epsilon naught, if you put that value, 1 by C equivalent will be x divided by epsilon naught A. Now epsilon naught A will cancel from both sides. Okay, so this is just a derivation. If you know the answer directly, if you know the formula, you can apply it. Those who don't know, okay, this is the process to solve from the beginning. And if you I will establish the rule after I solve it. Okay, minus t plus y. Okay, so x cancels, so this side we have 0. So and this goes to here, t minus t by k equals to y, or t into k minus 1 by k equals to y. Okay, or what we can do, let's not complicate it here. We are trying to find the dielectric constant, right? So take this one on this side, other one on the other side. So t minus y equals to t by k, right? Have I made any mistake? No. So k equals to t by t minus y. Okay, now let's put that value over here. So we have found the formula. You can remember this equation or this equation, whatever is your up to you. Otherwise you have to do this long derivation to find it. Okay, there is no other shortcut for this question. The shortcut is to remember this formula. Okay, there is no other shortcut. You cannot compare the capacitance of this and that. That does not work in this way. Okay, but you have applied this formula. So capacitance dielectric constant is basically T is 4 10 to the power of minus 3. Here also 10 to the power of minus 3. So we are not considering 10 to the power of minus 3 because that will eventually cancel, right? So separation of air separation is 3.5, right? Y is 3.5. So 4 by 0.5, so that is equals to 8. So the dielectric constant is 8. Okay, so you can remember this formula. Interesting question. Or you can remember this formula. Okay, the exact thickness that is increased. So if you increase it by y, that means already x is there, that thickness t is there. So t minus y is basically t by k. That is the formula you should remember. Okay. Next question. 8 drops of mercury of equal radii combine to form a big drop. The capacitance of the bigger drop as compared to the each smaller drop is. Now to answer this question, you have to remember that the capacitance of a spherical capacitor is directly proportional to its radius. So suppose 8 smaller drops, 2, 3, 4, 5, 6, 7, 8. 8 smaller drops, they combine to form a bigger drop of mercury. So each of them has a radius, say small r. Okay, so what is constant here? The volume is constant. Total volume of the, after they combine, that volume should be the volume of the new mercury. So what was the volume of one small drop? Volume of one small drop is 4/3 pi r cube. And how many drops were there? There were 8 drops. Okay, and that should be equals to the volume of the bigger mercury. Okay, so it will be 4/3 pi capital R cube. So 4/3 pi cancels. So we get capital R cube equals to 8 small r cube, or r equals to 2 small r. Now as I said, capacitance is directly proportional to radius. Okay, so as we see that radius is getting double, the radius of this bigger sphere is double that of the smaller sphere, any one of the smaller sphere. So if you compare their capacitance, the capacitance of the bigger sphere will be 2 times that of the small sphere. Okay, so the capacitance of the bigger drop as compared to each smaller drop is 2 times. Okay, next question. An electrician requires a capacitance of 6 microfarad in a circuit across a potential difference of 1.5 kilovolt. Very, very important. So the voltage required is 1.5 kilovolt. Okay, a large number of 2 microfarads capacitors which can withstand the potential difference of not more than 500 volt are available. The minimum number of capacitors required for this purposes. So we have 2 microfarad capacitors and 500 volt is the capacity of each of them. Now you might say that, sir, this is easy. Okay, if I connect 2 microfarad in parallel, then what is the equivalent resistance? If we connect 3 in parallel, the equivalent resistance is 6 microfarad. Okay, voltage will be added. So 1.500 volt plus 500 volt plus 500 volt, so 1.5 kilovolt. So that is also satisfied. So this will be the answer. 3 minimum is required. No. So when they are connected in parallel, you have to remember that the voltage is not added. Okay, charge gets distributed, voltage remains constant. So if you connect these 3 capacitors like this, even though the equivalent capacitance is 6 microfarad, but your circuit will fail. Why? Because the equivalent voltage that it can withstand is only 500 volt. Okay, because they are connected in parallel, so the common voltage will be the maximum voltage it can withstand. Common voltage will be 500 volt because each of them can withstand only 500 volt. So as soon as you connect it into 1.5 kilovolt, the circuit will break. Okay, so this is not the answer. If you think this is not super easy question, but it is not super difficult question as well. So first we have to think in terms of voltage. So first we have to adjust the voltage such that it can withstand the given input voltage. So 1.5 is the given input voltage and 500 volt is the maximum limit of one single capacitor. 1.5 kV means 1500 volt and one can withstand 500 volt. So at least we first have to consider that 3 capacitors we need to connect in series. Okay, so 3 capacitors first we have to connect in series. Okay, so that this combination can at least withstand the 1.5 kV. Now this is not 6 microfarad, by the way. In case of series combination of capacitor, they do not get added, they get added by 1 by factor, right? Reciprocally, they get added reciprocally. So what is the equivalent capacitance of these 3 capacitors? Equivalent resistance will be 2 by 3, right? All of them are equal, 3 of them are in series, so the equivalent capacitance will be 2 by 3 microfarad. Okay, so this is the minimum requirement. This is the first stage of solving this question. So this combination is required to withstand the 1.5 volt. Now we will combine this combination, okay, in parallel, okay, to increase the capacitance. Why? If we connect them in parallel, their capacitance increases. So if we connect them in parallel, their capacitance will increase. Okay, right? So we have to connect them, suppose n times. We have to connect them in n times. Okay, so n times if we connect them in parallel, what will be the total capacitance? That capacitance of one single of this joint is 2 by 3. So what is the capacitance of n such combinations? It will be n into 2 by 3. Right, series parallel combination, so it will be multiplied. So we are increasing the capacitance now. And what is our target? Our target is 6 microfarad. So the n should be chosen such that the result is 6 microfarad. So from there you get n equals to 6 into 3 divided by 2, that is equals to 9. So we need minimum 9 capacitor to achieve this both voltage as well as capacitance. So this is a very, very interesting, important question. So if such question comes in your KCET exam, be prepared. Don't answer without using your brain. Okay, first we have to balance the voltage, then we have to balance the number of capacitor. Now this is a question. In the figure, charge on the capacitor is plotted against the potential difference across. So this is a charge and this is the potential. okay, difference across the capacitor. The capacitance and energy stored in the capacitor are respectively. So first we have to find what is the capacitance, second we have to find what is the energy stored. So how to do that? First, what is the at 200 coulomb microcoulomb charge, it is microcoulomb, at 120 microcoulomb charge the voltage is 10 volt. So we know that it will be capacitance equals to Q by V. Okay, capacitance equals to Q by V. Q is 120 microcoulomb and V is 10 volt, so it will be 12 microcoulomb. Okay, so 12 microcoulomb is the capacitance. Okay, so either A or B is the correct answer. Now we have to calculate the energy stored. You can calculate the energy stored in multiple ways. Okay, the easiest is half CV square. Okay, if you don't remember what is the relationship between Q and V, other way is to calculate the area under this graph. Okay, area under this graph will give you the energy stored as well. So energy of this under this graph is half CV, half QV. Okay, so that is half into Q is 120 and V is 10, so it will be 60, so 600 microjoules. Okay, 600 microjoules. Why? 120 is given in microcoulomb, so 600 microjoules times is the energy stored and 12 microcoulomb is the capacitance. Easy question. Next question. The figure gives the electric potential. I am coming to the figure. The figure gives the electric potential V as a function of distance through 4 regions on x-axis. Which of the following is true for the magnitude of the electric field E at these regions? So here is the given graph. So you have to calculate where is the electric field is most, where the electric field is less, like that. So as you can see, what is the relationship between potential and electric field? So this is the potential. Okay, and this is the how it is changing with distance. So we know that electric potential, the relationship between electric field and electric potential is given by E is equal to dV by dx. There is a negative sign, but for now I am ignoring that. So we have to calculate how fast the potential is changing with respect to x. That will give you the highest electric field. Now you see that at this point and at this point electric potential is constant, so dV is constant. So if V is constant. If V is constant, dV is 0. If x is constant, dx is 0. Similarly, if V is constant, dV will be 0. So electric potential for these 2 points, that is VA and EA is equals to 0, EC equals to 0. Okay, now in this region V is increasing. Okay, so V is increasing means electric field will decrease. Negative sign, there is a negative sign here. So now we have to consider the negative sign as well. So V is increasing means electric field will decrease. So dV is positive means x is always positive, x is increasing, right? 1 to 2, x is increasing. So V is increasing means dV is E is decreasing. So here electric field will be not 0, but electric field will be negative. EB is negative. And here electric potential is decreasing, electric potential decreasing means electric field is increasing. So ED is positive. Okay, ED is positive. So let's see what is the combinations are given. Now if you see that EA and EC both are 0, so EA will be equals to EC. No doubt about that, right? So either so only one option. Okay, you don't even need to consider how and why it is changing, who is correct or not. So EA equals to EC is given only in one option. Here it is given EB equals to ED, which is not correct. Okay, so EA equals to EC is given in only one option, so you don't need to even consider positive, negative, increasing, decreasing, bigger, smaller. Only thing you should need to consider that EB is equals to EC. Only these two are equal because both of them are 0. So option D is is correct. Next question. Figure shows. So from this chapter, as you can see, a lot of figure based questions might come for your final KCET exam. So figure shows 3 points A, B and C in a region of uniform electric field E. So A, B and C in an uniform electric field E. So electric field is uniform. The line AB is perpendicular to BC. The line AB is perpendicular to BC, so that is, this angle is 90 degrees. Okay. Then which of the following holds good? VA, VB and VC represents the electric potential at this point. So VA, VB and VC are the electric potential. Now you see that, so this is perpendicular, means this is actually the perpendicular to the electric field as well. So this represents a equipotential surface. So equipotential surface means VA must be equals to VB. Okay, and as we are moving in the direction of electric field, okay, as we move in the direction of electric field, electric potential decreases, right? Negative relationship, if E is as you are moving in the direction of electric field, V decreases. E always points in the decreasing electric potential. So VC must be less than VA and VA must be equals to VB. Okay, that should be the relationship. Now let's see how it is represented in the answer. So VA equals to VB, about no doubt about it, and this combination VA VB should be greater than that of VC. So VA equals to VB and it is greater than VC. So option D is correct in this case. So you have to be careful, don't fall for any trap. VA is definitely equals to VB. This is an equipotential surface and they both are greater than that of VC, because VC is in the direction of electric field and in the direction of electric field potential decreases. Next question, a dipole of dipole moment P and moment of inertia I is placed in an uniform electric field E. If it is displaced slightly from its stable equilibrium position, the period of oscillation of the dipole is. So now what is the torque? First we have to calculate the torque. Torque is PE sin theta. Right, torque is P sin theta. Now for small displacement, if it is displaced by a small amount, okay, displaced slightly, then we can say that theta is very small. So electric dipole, if you displace it by small amount, then we will say that the displacement is very small, means theta is small. So theta small means if theta is small, then what we know? We know that sin theta nearly equals to theta. Obviously theta expressed in radians. This is only valid when theta is expressed in radians. But anyway, we are not interested in that. We are only interested in writing theta over here. Now, so this is the torque acting on the dipole. Now there is another relationship from the rotational motion chapter. So this is a lightly mixed concept question. From the rotational motion chapter, we know that torque is also represented by I into alpha. I is moment of inertia, alpha is angular acceleration. Torque is what? Torque is the rotational equivalent of force. Right, force equals to ma and torque is equals to I alpha. I is what? I is the rotational equivalent of mass. Right, so here we will use that. So I into alpha. So what is alpha is equals to? So alpha equals to Pe by I into theta. Okay, so we have established the rotational equivalent equation for simple harmonic motion. In simple harmonic motion, if you remember, acceleration equals to omega square into x. There was a negative sign, but if you ignore the negative sign, you will get acceleration equals to omega square x. From here we calculate omega and time period was 2 pi by omega. Right, this was how we used to calculate time period, if you remember. So if we use the same logic over here, we can calculate omega square. So this is the rotational equivalent. So rotational equivalent means same thing will happen, omega square theta. Okay, so omega is basically equals to square root of Pe by I. This is the omega square. So omega square means omega will be square root of P by I. So what is time period? Time period is 2 pi by omega. or it will be 2 pi square root of I by PE. And this is the formula value for time period. So 2 pi I by PE is the answer for this question. Let's move on. The difference between equivalent capacitance of two identical capacitors connected in parallel to that in series is 6 microfarad. The value of capacitance of each capacitor is. So when two equal capacitors are connected in series, their capacitance is C by 2, equivalent capacitance. If they are connected in parallel, their equivalent capacitance is 2C. Okay, so if n equal capacitors are connected in series, their equivalent capacitance is C by n. If they are connected in parallel, then it increased by n times, so it will be n into C. Always remember this, right? So because only two capacitors are there, so their equivalent capacitance will be 2 into C. In parallel and in series it will be C by 2. Obviously 2C will be greater than C by 2, so that is why we are doing it, and the difference is given here as 6. Okay, now we have to take C common. You will get 2 minus half equals to 6, or C into 2, 4, 3 by 2 equals to 6, or it will be 2, so C equals to 4 microfarad. Okay, so C is 4 microfarad. Easy question. Only thing, if you know this is the shortcut. If you know it, you can use it directly. Next question. Two metal plates are separated by 2 centimeter. These potentials of the plates are minus 10 volt and plus 30 volts. Okay, the electric field between the two plates is. Okay, so what is the electric potential? So they are separated by 2 centimeter. 2 centimeter means 2 into 10 to the power of minus 2 meters. Always convert them into meters. So one of them is plus 30, another one is minus 10. So if the electric field always points in the direction of decreasing potential, so what is the electric field? Electric field is delta V by delta X. So delta V is 30 minus minus 10 divided by 2 into 10 to the power of minus 2, or it will be 40 divided by 2 into 10 to the power of minus 2, or it will be 20 into 10 to the power of 2, that is 2000. Okay, 2000 volt per meter. Okay, 2000 volt per meter. Okay, now let's move on to the next question. The equivalent capacitance between A and B is. So here A and B are 2 points. We are trying to find the equivalent capacitance. How to do that? First we have to identify which of them are connected in series and which of them are connected in parallel. So as we can see that right now this is connected individually to all the parts. So first we have to solve the upper part. Obviously this much is clear. If we solve the upper part, then we can check whether how it is connected to the lower part. So how upper part is connected? Now if you see that here we have 200 picofarad, they are connected in series. Okay, so 200 picofarad connected in series means the equivalent capacitance will be half of them, right? Two equal capacitors in series. As I said, in series capacitance decreases, so the equivalent capacitor will be a 50 picofarad capacitor. Okay, so you can cancel them. So now we have a 50 picofarad capacitor and another 50 picofarad capacitor. They are connected in parallel. So these two are connected in parallel means what is the equivalent capacitance? The equivalent capacitance will be sum of them. In parallel they gets added. So 50 plus 50 will be 100. So now we have 100 picofarad, right? These two at A, and this one at the bottom one, that is here, that is B. So 100 picofarad, 50 picofarad. Now if you see that they are connected, even though they are looking like connected in parallel, they are actually connected in series because this is our point. So you can bend the circuit and you can make them look like this, right? 100 into 50, A, B. Okay, 100 50. So they are basically connected in parallel. Sorry, not parallel, series. Okay, because you can start here and you can go to the second point without lifting your pen. That means they are connected in series. So what is the equivalent capacitance? 100 into 50 by 100 plus 50, direct formula, that is the C equivalent, right? So it will be 100 into 50 divided by 150. So 0 0 cancels, 5 3 5s are 15. So 100 by 3 or 33.33. So here we have 100 by 3 directly given. So 100 by 3 picofarad is the answer. Okay, now let's move on to the next question. A capacitor of capacitance C charged by an amount Q is connected in parallel with an uncharged capacitor of capacitance 2C. The final charges on the capacitors are. Okay, so first we have a capacitance C charged by an amount Q. So capacitor C charge is Q. Okay, now you connect them in parallel with another capacitor having capacitance 2C. This has charge 0. Okay, now when you connect them in parallel, the potential should be constant, total charge also should be constant. Okay, so how we can calculate it? So initially, what is the potential of the system? Initial potential was V is equal to Q by C. Okay, so now final potential, assume that the final potential of the system, obviously some charge will come over here, some charge, say Q dash charge or Q1 charge comes over here. Okay, so what is how much charge left here? Q minus Q1. Now the final potential, suppose whatever is the final potential V dash, that should be same for both capacitors. That is our starting point. So final potential should be same for both capacitors because they are connected in parallel. So when they are connected in parallel, the final potential should always be constant. Okay, so final potential, say V dash. So what is V dash? V dash is Q minus Q1 by C, and that should be same for the other one. So Q1 by 2C. Okay, so C cancels, here is 1. So 2Q minus Q1 equals to Q1. Sorry, minus 2Q minus 2Q1 equals to Q1. So 2Q equals to 3Q1. Okay, or Q1 is basically 2/3 Q. So what is the charge of the second capacitor? Charge of the second capacitor Q minus Q1, or original capacitor rather, charge on the original capacitor is basically Q minus 2/3 Q, that is 1/3 Q. Okay, so 1/3 Q and 2/3 Q. Okay, 1/3 Q and 2/3 Q is the answer. So be careful, the order is very careful. In some cases maybe they will give you wrong order as well. So the original capacitor will have 1/3 Q and the new capacitor will have 2/3 Q. Now because of higher capacitance, it will have higher charge. So that is a way to check if your answer is correct or not. Now question number 18. A particle of mass m and charge q is placed at rest in uniform electric field E and then released. The kinetic energy attained by the particle after moving a distance y is. Okay, particle. Now it might look like it belongs to magnetic charges question, but it is not moving charges and magnetism chapter. It is basically related to electrostatic potential and capacitance only. So this question, when it is coming as a whole part of the question, you might think this has to do something with Lorentz force, etc., but actually it is not. Okay, how can we do that? So charge is Q. Okay, the easiest way to do it is charge is Q. Okay, electric field is E. Okay, so what is the force acting on it? Force acting on it, Q into E. The force acting on the charge is Q into E. So now if you move it by a distance of y, how much work you are doing? The work you are doing is F into Fs cos theta, but here they are moving in the same direction, so it will be F in, it is moving in the direction of electric field, right? So it will be F into y or Q E y. So this is the work done. Now what is work energy principle? Work energy principle says that whatever is the change in kinetic energy, that is the work done. Now initial kinetic energy was 0 because it was starting from rest, so the final kinetic energy will be Q into E into y. So Q into E into y, option A is correct answer. Don't get confused, don't fall for the trap. Easy question, not super difficult. You can answer it like this, or there is another way to answer this question, that kinetic energy or energy stored or work done, whatever it is basically work done is basically Q into V. This is the direct formula, right? Now V we do not know. V we do not know, but we know that E is V by Y. dV by dy, but here V represents the change in potential energy, right? So change in potential energy equals to E is equal to V by Y. So V is equals to E into Y, or you can use this as well, whatever you are comfortable with, QEY. Okay, I feel this is the safest one, easier one. This is slightly tricky one. Okay, you might confuse here, but whatever you are comfortable with, you can use both method and you will get the both same answer. Now next, a system of two charges separated by a certain distance apart stores electrical potential energy. If the distance between them is increased, the potential energy of the system is. System of two charges separated by a certain distance. So Q1, Q2, and separated by a distance, say R. Okay. So what is the electrical potential energy of this system? The electrical potential energy of this system is KQ1 Q2 by R. Okay, remember that it is similar to the potential but with an extra charge. It is very familiar, similar to Coulomb's formula, but Coulomb's formula we had a square, here we do not have the square. That is the basic difference. Okay, now if the distance between them is increased, the potential energy of the system. So if you increase the distance, suppose now if you have gone to the new distance, say capital R, then the new potential energy will be K Q1 Q2 by capital R. So as it is inversely proportional, we can say that if you increase the distance, potential energy of the system will decrease. Okay, so it will decrease in any case. Okay, it decreases in any case. The potential energy of the system, which is a scalar quantity by the way, if you are thinking, so it will decrease in any case. Now next question, mass of 1 kg carrying a charge of 2 coulomb is accelerated through a potential of 1 volt. The velocity acquired by it. So mass is 1 kg, charge is 2 coulomb, potential is 1 volt. So what is the work done? Again, work done or kinetic energy. Work done is equals to kinetic energy. Kinetic energy is half mv square, and that is equals to Q into V. Okay, so work done is half mv square, kinetic work energy principle, and that half mv square should be equals to the work done. What is work done? Work done is if you moving a charge in a potential, it will be Q into V. So Q is given 2 coulomb, voltage is given 1 volt, and m half mv square equals to 2. Now what is m? M is 1 kg. So v square equals to 2 into 2 divided by 1, that is 2 into 2, or v equals to 2 meter per second. So the speed of the charge is 2 meter per second. Okay, easy question. Now for the arrangement of the capacitors as shown in the circuit, the effective capacitance between the points A and B is capacitance of each capacitor is. Okay, so capacitance of each capacitor is 4 microfarad. Okay, it is given here. Now you have to find the equivalent capacitance between A and this B, which is located some like this. Okay, so you might say that okay, this capacitor is out of the loop, so we do not need to consider this. So but no, first we have to consider this 4 microfarad only. So how we can do that? So we have to redraw this structure slightly, okay? So if you see, this is 4 microfarad, then we have, so this 4 microfarad I am, because this is connected like this, I am bringing it here. Okay, I draw this 4 microfarad at the center. Then we will see that how we can ignore that 4 microfarad. It can be ignored, but because of a different reason. Now let's draw this circuit. Now this 4 microfarad, I am drawing it like this. Anything familiar? Anything looks familiar here? And this microfarad, I am drawing it like this. Yes, those who have guessed it, correct. Okay, so this is like Wheatstone bridge. Okay, similarly, this one also I am drawing it like this, and this one not like this. This is this, and then this and this. Okay, so this is just nothing but a Wheatstone bridge. Okay, but in terms using capacitor. So this is our point B, this is our point A. So you have to have a keen eye to answer such questions. Okay, now because it's connected like a Wheatstone bridge formation, and if you see 4, 4, 4, 4, so if you convert them into equivalent resistances, we know how to convert it. In case of AC we can do it, but anyway, if you consider them to be just simple capacitors as well, okay, because the ratio of the capacitance is same, that is 4 by 4 is 1, 4 by 4 is 1 here as well, so there will be no charge or no potential, nothing will be here across this capacitor. So you can simply remove this capacitor. Okay, so now we see that this 4 and this 4 are connected in series. This 4 and this 4 are connected in series. So two equal resistance connected in series, the value is half. So 2 microfarad and again another 2 microfarad. Now they are connected in parallel, so parallel they gets added, so 2 plus 2 is 4, so the equivalent capacitance is 4 microfarad. So all comes down to 4 microfarad. So if you see similar question in any other problem, say they have given the value, say 100 or 5 or 6 or 7, whatever value they will give, you should know that after solving it, it should come to the same value, only if it is like this. The work done to move a charge on an equipotential surface is 0. This is easy question, okay, a slightly older question, but we have solved this question in our PU board exam as well, right? So equivalent potential is 0. Two capacitors of 3 microfarad and 6 microfarad are connected in series, and potential difference of 900 volt is applied across the combination. They are then disconnected and reconnected in parallel. The potential difference across the combination is. So very, very interesting question. So first, 3 and 6 microfarad are connected in series. So once they are connected in series, they will have the same potential, same charge stored into them, okay, and they are connected across 900 volts. So first we have to find the equivalent capacitance. Equivalent capacitance is 3 into 6 divided by 3 plus 6. Okay, in series means opposite to that of resistance. So 3 into 6 divided by 9. So 3 3s are 9, 3 2s are 6, so it will be 2 microfarad. 2 microfarad is the equivalent resistance. So what is the charge stored? Charge stored, Q is equal to C equivalent into potential applied, that is 2 into 900. Microfarad does not matter here. Okay, so this is the charge stored. Microcoulomb you can write. Okay, why so charge does not matter? Because they will cancel anyway. So this is the charge stored in each of them. Okay, this is the charge stored in each of them when they are connected in series. Now when you connect them in parallel, so what is the total charge, by the way? So total charge, this is each of them, both has same charge. So total charge is basically 2Q. Total charge is twice of this. This is the, when they are connected in series, each of them will have the same charge. So this is Q, this is Q. So total charge of the system is 2Q. So that will be another 2 times, so 2 into 900. Okay, so this is the charge of the total charge of the system. Now once you connect them in parallel, the charge will no longer remain the same. Okay, but total charge will remain still this. So suppose the charge of this is Q1, charge of this is Q2, and the potential of the system is, say, V. We are trying to find V. Okay, but this is equals to Q1 plus Q2. You have to remember this. Okay, we are trying to find the potential V. This is one of them is 3, one of them is 6. Now what is Q1? So what is Q1? Q1 is 6V, potential is same. What is Q2? Q2 is 3V. Okay, now if you add these two, what you get? Q1 plus Q2 equals to 3 plus 6, 9V. Okay, 9 microfarad is there, but again, as I not considered here, you will not be considering here as well. So what is Q1 plus Q2? Q1 plus Q2 is this. So Q1 plus, so 9V equals to 2 into 900. Okay, so 9 cancels, you get 100. So 2 2s are 4. So 4 into 100, that is 400. So V is equals to 400 volt. So you get the answer, option D, 400 volts. Slightly lengthy, but not difficult. Okay, in my opinion, this is easily solvable if you practice this type of questions often. Okay, and if you want to practice, obviously you have to join our Abhyas KCET test series, where we are giving you mock test. Okay, almost every day, physics, chemistry, maths and biology as well. So those who are appearing for PCMB subjects, they also get the biology option. Otherwise, physics, chemistry, maths, everything is covered here. Now 24, a system of two capacitors of capacitance 2 microfarad and 4 microfarad is connected in series across a potential difference of 6 volt. Okay, so two capacitors of capacitance 2 and 4 microfarad is connected in series across a potential difference of 6 volt. The electric charge and energy stored in the system are. Okay, so we have solved one similar question. Only thing is that here this is a straightforward question. 2 microfarad and 4 microfarad. 2 and 4 microfarad connected in series across a potential difference of 6 volt. Now here microfarad is important. Previously, because we had just comparing, so microfarad conversion was not required. Okay, anyway, it will you can write it micro coulomb or microjoules. So even though the conversion is not super important. Now what is the equivalent capacitance? Equivalent capacitance is 2 into 4 by 2 plus 4. So that is equals to 8 by 6. So it will be 4 by 3. So 4 by 3 is the equivalent capacitance of the system. What is the charge stored? Charge stored is simple. Charge stored is half 4 by 3 into the voltage applied, that is 6 volt. So it will be 8 microcoulomb. So 8 microcoulomb is the charge stored. So you can directly say, okay, I know 8 microcoulomb is the charge stored. I do not need to consider the energy. So energy, anyway, how to calculate the energy? If you want to calculate the energy is basically half, not CV square. CV square formula we already know, but in this case C is complicated, so half V square, you have to do the V square anyway, so it will be Q into V, half Q into V. So half into Q is 8, V is 6, so it will be 24 microjoules. Okay, so energy is half microjoules. To my energy is also matched. In case they give you same capacitors, you have to know how to find the energy as well. So half CV square is okay. You can use half CV square as well, but QV is easier. Q already calculated. If only energy is required to calculate, then half CV square would be easier. 2 point charges A equals to plus 3 nanocoulomb and B equals to plus 1 nanocoulomb are placed 5 centimeter apart in air. The work done to move charge B towards A by 1 centimeter. Wow, easy question. So first, what is the potential energy of the system 1? Potential energy of the system 1 is K Q1 Q2 by R1. Okay, now if you move them by 1 centimeter, okay, initially they are in 5 centimeter in air, so let's put the values. So K Q1 is 3 nanocoulomb, another one is 1 nanocoulomb, and they are separated by a distance 5 centimeter. 5 centimeter means 10 to the power of minus 2. Okay, we'll put the value. Now what is the final potential energy? Final potential energy is same K into 3 into 10 to the power of minus 9 into 1 into 10 to the power of minus 9 divided by, now the distance is, now what happens is that the distance is 1 centimeter less, okay, because we have moved the charge towards A by 1 centimeter. So the distance is now 4 centimeter. Okay, clear? Because we have moved the charge, so initially they were at 5 centimeter, we have moved one of the charges by 1 centimeter. So what is the new distance? The new distance, the initial distance was 5, now new distance is 5 minus 1, so that is 4. Okay, so the new distance is 4 centimeter. Now you have to find the difference between these two energies, that is the problem. Okay, so let's solve it. So it will be, so U, delta U equals to final energy minus initial energy. Okay, that is the formula. So K into, most of the things will be common, 3 10 to the power of minus 18, 3 in, first U2, right? So 3 into 10 to the power of minus 18, we'll put the value of K in some time. Okay, 3 into 10 to the power of minus 18 divided by 4 into 10 to the power of minus 2 minus 3 into 10 to the power of minus 18 divided by 5 into 10 to the power of minus 2. So if you just simplify it, what will happen is that this will go up and it will become plus. Similarly, this will go up and it will become plus. So you will get 10 to the power of minus 16 here, minus 16 over here, and 3 by 4, 3 by 5, right? Now 3 into this thing comes common, so 9. Now we are putting the value of K. Okay, now 0 enters, so 10 to the power of minus 16. Okay, don't waste too much time on all these values from the beginning. Okay, and if you multiply it, again, not a good idea always. So 4 5s are 20 and 5 minus 4. Okay, so you get 3 9s are 27, and here you will get, they will cancel, you will get 1 by 20, so 27 by 20 into 10 to the power of minus 16 plus 9, that is minus 7. Okay, so what is the value? 27 by 2 is 27 by 2 is 13.5. So 13.5 divided by 10, it will be 1.35. So it will be 1.35 into 10 to the power of minus 7. 1.35 into 10 to the minus 7 joules. So as you can see, this is the correct answer. Okay, how I calculated this without using calculator, using my mind only. Okay, my mind is super strong, right? I am a magician. No, I am not. I can calculate it faster. So this this is a very, very important trick for all of you to know. If you are watching up to this point, don't forget to mention that in the comment below. Okay, I know many students start watching, then they left in the in between video. So if you have reached this point and if you are watching this shortcut, then please let me know in the comment below. So 27 by 20, how I have done it, I have divided it into two parts. 27 by 2 into another 10, right? I can do that. Now 27 by 2 is what? 27, what is the next number? 28. So 28 by 2 is 14, right? 28 by 2 is 14. So 27 by 2 should be 0.5 less than that. That is 13.5. 28 means 14. So 27 will be 13.5. So 13.5 is the 27 by 2. If you are very good at maths, 27 by 2 with 13.5 you can directly do it. Now that is divided by another 10. So this part is taken care of. This part is taken care of. So we are dividing it by another 10. That means it will be 1.35. Okay, this thing, entire thing I did it in my mind, and I don't need calculator. I am now explaining it to you. If you practice this, you can also do it, right? Now let's move on to the next question. The minimum value of effective capacitance that can be obtained by combining three capacitors of capacitors. Capacitance is 1 picofarad, 2 picofarad and 4 picofarad is. So minimum value of effective capacitance. Minimum value of effective capacitance means they are connected in series only. So whenever it is minimum, they are connected in series. Whenever they are considered maximum, it will be connected in parallel. Okay, so 1 pico, 2 pico, 4 pico. 1, 2, 4, they are all connected in series. So minimum resistance we are trying to find. So 1 by C equivalent is equals to 1 by 1 plus 1 by 2 plus 1 by 4. There is no shortcut here because three capacitors are there. LCM is 4. So 4 ones are 4 plus there is 2. So 2 twos are 4 plus 2, and then we have another 4. So this will be 1 only. So it will be 6 plus 1, 7 by 4. Now remember that this is not the answer. Here we have 1 by C equivalent, so you have to take the reciprocal of that. So C equivalent is equals to 4 by 7. So the answer is 4 by 7. Okay, so 4 by 7 picofarad is the answer. Now I have seen students after solving this much, they forget to take the reciprocal and make it wrong, right? Now 27. Nature of equipotential surface for a point charge is it's a sphere with charge at the center of the sphere. So it's a sphere, charge at the center of the sphere means option B is correct. Next question. A particle of mass 1 gram and charge 1 microcoulomb is held at rest on a frictionless horizontal surface. So mass is 1 gram, charge is 1 microcoulomb, and it is held at rest on a frictionless horizontal surface at a distance 1 meter from fixed charge of 2 millicoulomb. So at a distance 2 meter, so we have another charge, fixed charge. This is 2 millicoulomb. Okay, and this one is 1 microcoulomb. Okay, the distance is 2 meters. So in such cases, try to draw the diagram. That will be very easy. So this is 2 millicoulomb and another one is 1 microcoulomb, and the distance is 2 meters. Okay, the particle is released. It will be repelled. The speed of the particle when it has a distance of 10 meter from the fixed charge. So when you are releasing it, it will start moving with some velocity. Initially it will be 0 and slowly it will start accelerate, and it will gain some velocity. So the velocity you have to calculate after it reaches at a distance 10 meter from the fixed charge. So 10 meter from the fixed charge. Okay, 10 meter from here only. Okay, how to do that? So again, work energy principle. So what is the initial potential energy of the system? So initial potential energy of the system U1 is equals to K Q1 Q2 by R. So K is 9 into 10 to the power of 9. Q1 is 2 millicoulomb, milli means 10 to the power of minus 3, and here it is 1 microcoulomb, microcoulomb means 10 to the power of minus 6, 1 microcoulomb, so I am not writing any value over here just to save some space. Distance is 2 meters, so 2 over here, 2 cancels, 10 to the power of minus 3, minus 6, that is minus 9, and 10 to the power of 9, so initial potential energy is 10 joules. 9 joules. Okay, so initial potential energy is 9 joules. Now final potential energy, everything on the top will remain same, on the bottom, so the except 2 will be here, and there will be 10 meters. Okay, so 10 meters, so it will be 1.8 joules. Okay, 1.8 joules. The potential energy of the system is decreasing. So how much, by how much it is decreased? So delta U, that should be the work done, and that should be half mv square. Okay, that should be equals to the change in the potential energy. So 9 minus 1.8, that will be 7.2. Okay, 7.2 is the half mv square. Now this is not over yet. Here the mass is given in grams, so you have to convert it into kilograms. Okay, so you have to do what? Half into 1 gram means 1 gram means 10 to the power of minus 3 kilograms, right? 1000 gram is 1 kg, so it will be 10 to the power of minus 3 kilograms into v square equals to 7.2. So now you have to take this on the other side. So v square equals to 7.2 into 2 into 10 to the power 3. Okay, so 7.2 into 2 is 14.4, 144. So it will be 14400. Okay, 14400. Why 00? One of the decimals will be consumed, so the remaining 2 zeros will be here. So V is equal to 120 meter per second. Okay, 144 means 12 square, and 00 means 10 square. So 12 into 10 is 120. So answer is 120. Have I made any mistake? I have not made any mistakes. So maybe they have not given the correct answer over here. Okay, I have calculated everything correctly. So maybe this is the correct answer. This is the closest answer. So we will take this as the correct answer. Okay, neither 60 nor 90 nor 180 are the closest. So 100 is the closest. We will take 100 as the closest answer. So in case if you see the answer such that after solving you don't get match the answer, you have to take the closest answer for that question. Okay, now next question. 4 metal plates are arranged as shown in the capacitance between X and Y. So here we have 4 metal plates as they are arranged like this. Okay, you have to calculate the capacitance between X and Y. Okay, now if you see that these 2 points are connected directly, so they are basically you can say, but there is no connection here. So they are at the same potential. So area of them is A and distance between each of them is D. So this is D, this is also D. Now if you see that this bent part is not doing anything. This bent part is not doing anything. It is just kept as some random thing inside the capacitor plate. Capacitor plate is connected like this, right? So this is the capacitor plate. So basically you are doing the capacitor. This is the actual capacitor, right? So this is nothing. This in between part you can ignore. You can simply say that I have a capacitor of distance 2D, area A. Okay, there is no dielectric medium in between them. So the capacitance is epsilon naught A by 2D. Okay, this is the capacitance. So epsilon naught A by, I don't know, either this problem is wrong or the option is wrong. The answer will be epsilon naught A by 2D, as this does not play any role in the capacitor. If this is connected from this side, then you can say, okay, this is a capacitor, this is a capacitor, this is a capacitor, and there is no dielectric constant as well. So this one you can just simply ignore. This is not at all related to the capacitor. So this will be the answer for this question. Now let's move on to the last question. A parallel plate capacitor is charged and then isolated. The effect of increasing the plate separation on the charge, potential and the capacitance respectively. So you have a parallel plate capacitor, it is fully charged, and then you have increased the distance between them. So first of all you have to remember that the charge remains constant. Charge is conservative. You cannot increase or decrease the charge of an isolated system. So this is an isolated system. Even if you are increasing the distance between them, system is still still isolated, so charge will remain constant. Okay, so as you can see, 3 of them are giving charge constant, so obviously out of these 3 one of them is correct. Now if you increase the distance, if you increase the distance, the capacitance will decrease, right? Capacitance is inversely proportional to the distance. Capacitance is inversely proportional to the distance. Now if capacitance decreases, voltage will increase. Voltage is directly proportional to the distance. So more the voltage distance, higher is the voltage, so voltage will increase, whereas capacitance will decrease. So constant, charge is constant. Okay, potential increases, capacitance decreases. So this is the correct answer. Okay, option B. So I hope you enjoyed today's session. If you have any doubts, any questions, don't forget to mention that in the comment below. And if you have not yet subscribed to our channel, don't forget to subscribe to our channel. Also join our WhatsApp group. We are sharing all the latest PDF of our lectures in our WhatsApp group, so don't forget to join there. And obviously for practice, you have to join Abhyas KCET test series, where we are doing a lot of mock test before your KCET exam is coming, right? So I will see you in next lecture. Till then, bye.